Hello.
Yeah, now it is visible, sir, to all the participants.
Okay, okay. So let us start with the next.
Everyone see the screen? Yes, sir. Yes, sir. Okay. So you continue, sir.
Okay, let us start with the second simple exercise. It will be to evaluate an exponential of a function, exponential of a variable. So we all know that e to the power x can be approximated as 1 plus x plus x square by 2 factorial plus x cube by 3 factorial and so on. So now let us write a program which will do this evaluation for how many number of terms we ask it to do. So the last, rather the n plus 1th term will be x to the power n divided by n plus 1 factorial. So this is the, so essentially we are trying to find out summation n equal to 0 to infinity, or not, in this case not infinity, n x to the power n divided by n factorial. This will not be n plus 1 factorial, in fact this will be n factorial. Okay, so we want to evaluate this summation. So what are the various strategies? Let us write here first and then we can go to the program later. So one way to do it is I say some variable s is equal to 0. Then I do for I in np dot a range going from 0 to n. Then I say s equals s plus x to the power I divided by a factorial. And I do this loop until I reach the last element and then I exit. And at the point of exit, S will contain this entire sum. So what is this meaning? So S equal to 0 means initially, suppose I write the I number over here. Okay. So loop number 0, the output should be 1 actually. Loop number 0, the output should be 1. So because, okay, let me write down the value of S, the value of x raised to I, the value of I factorial, and x to the power I divided by I factorial. So when I is equal to 0, which is when it is entering into this loop. So I hope it is clear what this means. I hope it is clear to all what this means. This will create an array which looks like 0, 1 all the way to n minus 1. Okay. So when I is equal to 0, it enters the loop. S is already 0. S is 0. But x to the power I. So what will be x to the power I? Suppose x is some integer, or not some integer, some number. It doesn't matter. So x to the power I will be x to the power 0. X to the power 0 is 1. I factorial. What is 0 factorial? 0 factorial also 1. So it will be 1. So s equals s plus 1. This will have what meaning? S equals old value of s, which is 0, plus 1. So s will then become, so s new I am writing over here, it will become 1. So now when it goes again into this loop for the second time, I will become 1 because this loop is already executed. So I will now become 1. So I is now 1. S has already become 1. X to the power, this will be x to the power 1. This will be 1 factorial. So this will be x to the power 1 upon 1 factorial. So S will be 1 plus x to the power 1 by 1 factorial. So now the value of s will become s to the power x to the power 1 by 1 factorial, and that will be stored in the variable s. So now s, when it comes back into the loop, will have the value x to the power 1 by 1 factorial. So now when I becomes 2, this will become x square, this will become 2 factorial, this will become x square by 2 factorial. Now it will be old value of s plus x square by 2 factorial. The new value of s will be x square by x by 1 factorial plus x square by 2 factorial. So then this will become x to the power 1 by 1 factorial plus x square by 2 factorial and so on. So you get the point. X is called as a sum accumulator. Because it is sort of accumulating the sum in itself. So a sum accumulator is always initialized with 0, and you can imagine that a product accumulator will be initialized as 1. Okay, but anyway, we don't bother about it for now. So this is how the gist of the loop will look like. Alternately, we know how to vectorize things. So I can also sort of vectorize the entire thing. So let me define I as np dot a range 0 n. So then I becomes, suppose n is equal to 6. So I will become 0, 1, 2, 3, 4, 5. Suppose n equal to 6. Right? So now I can ask the user for what x will be. So whatever x is, I can say that terms equals to x to the power I divided by I factorial. So what does it mean? It will broadcast this operator over all values. It will broadcast this x to all values of I. So if x is equal to suppose 1.1, so x to the power I will actually contain x to the power 0, x to the power 1, x to the power 2, x to the power 3, x to the power 4, x to the power 5. So if x is 1.1, then this will have 1.1 raised to 0, 1.1 raised to 1, 1.1 raised to 2, 1.1 raised to 3, and so on. And if I do this divided by I factorial, this will have divided by 0 factorial, divided by 1 factorial, divided by 2 factorial, divided by 3 factorial, by 4 factorial, and so on. Now why do I call it terms? Because these individual elements of the array are actually each of the terms in the exponential representation. Okay, in this particular representation, I have all the terms for at least n number of terms, right? Now I just need to simply sum all the elements of this particular terms array. If I do this, the output will be the sum that I want. Okay, let us go to Python because it will be clearer over there. Okay, so let me reset my kernel. It will erase all the variables and all because we want to start new. So we have reset everything. Now let me define, so I have to again import all the things. So import numpy as np. So let me call I equal to np dot a range 0 to 0, 6. Let's see what I is. And let us say x equal to 2. Let me do x to the power I. Let me call it temp equal to x to the power I. Let me see what temp is. So look, I was 0, 1, 2, 3, 4, 5. X was equals to 2. And temp is equal to x to the power I. So all the various elements of I have been operated onto x. So 2 to the power 0 is 1. 2 to the power 1 is 2. 2 to the power 2 is 4. 2 to the power 4 is 16. 2 to the power 5 is 32. Okay. Now np dot sum of temp is the sum over all the arrays. So 1 plus 2 plus 4 plus 6 plus 8 plus 16 plus 32 is indeed actually 64 minus 1, which is 63. You can do it yourself, or if you know how to make a sum of a geometric series, it is equals to 63. So now we know how to make this work. Let us make a new file. So before starting the file, it is good habit to write down the purpose of the file. P to the power x is 1 plus x square by 2 factorial plus x cube by 3 factorial and so on, right? Okay, so let us define the function first. So actually the function should take as an input. Okay, actually let us write the script first. From the script we will convert it into a function. So n equals 6. So I equals np dot a range 0 comma n. So it will have 6 terms. The last index will be 5. I mean, you have done this before also. Let us ask for what the value of x will be. Say it is x equal to 1.1. So then for I, so let us define s equals to 0. So s is the sum accumulator. Okay. So s equals to 0. So for I in other, for I in np range, okay, s equals s plus x to the power I divided by factorial of I. So now comes the tricky part. Where is the function factorial? The factorial is not a standard function. So just a cursory documentation search helps us to find where it is, and from experience I know where it is. So it is import scip.special as sp. Let us save the function, let us save the file as evaluation.py. So scip.special as sp. So sp is the alias for the import of the module scip, in which a set of commands is there inside special. Okay, so let us write here sp dot factorial of I exact equals false. Actually, no need to write exact equals false. So yes, after this, let us print so let us print what we should say n equals, then we have to print n e exact equals. So over here we have to write down the exact value of the exponential, and the exact value of the exponential is actually present inside the numpy package. So scip is another package like numpy, and scip contains various kinds of functions which are sort of overriding numpy oftentimes. So scip is a more advanced package, but we don't need them. So we import numpy as np. So we write here np.exp1. So e raised to 1 is the exact value of the exponential. Then we write the e approx. So that will be the value of s. Okay, so let's run this. So with but actually we have evaluated the approximate value of s at 1.1. So we should not write this as 1, we should write this as x e raised to 1.1. So let's run it. So the exact value is 3.004166, while the approximate value is 3.00125. Actually, let's see, when we increase the number of terms, let us make it 10. When we make it 10, the exact value is 3.004166 and the approximate value is 3.0041652. So as we all know, if you take larger number of terms, the whole thing begins to converge. Okay. Equivalently, I could have written down the error also. So I could have written here, instead of this, I don't want to write down the E exact. I just say n equal to this, the approximate value is this, and then I write error is n np dot exp 1 point, not 1.1 e raised to x minus s. So it's an error of 7.9 10 to the power minus 7. It's a very small error. Okay. Now let us see how to convert this particular thing into a script, into a function. So ideally we want to output simply the value of the exponential, or in this case the value of the sum from the function. And as an input we want to tell the function that I want so many number of terms in the approximation and I want to evaluate the exponential at this particular value of x. So we will cut this. So we just want these things to be in the main function, main script. So we will define e approx and the input will be the number of terms and the value of x. Again, I will tell you that this n and this x are different from the n and x in the main script. They have no function scope. These things have no function scope in this. I could have called them as alpha, beta, gamma, whatever you want. Okay. Let me paste whatever I had taken. Let me indent everything. So the for loop indentation also works like a function indentation. Anything after this for which is indented will be a part of the for loop. When once you escape this particular indentation, you go back into the function. When you escape that indentation, you get out of the function. And that should be obvious. I've been saying this. So for I in this, s equal to 0, s equal to s plus this, and that's it. It's a very simple way to convert that script into a function. Now, what do you think? This s, so if I run this, I have not returned anything. If you are very observant, you will see that this function has not returned anything. So if I run this, it will say the name s is not defined. It tells me an error in line 21. So line 21 is this, and it says s is not defined. But you might say, wait, s is defined over here. And like I said, the s defined inside this function is actually local to this function only. It is only when I return s inside this function, once I return s, it means whenever this e approx function is called with a value of n and with a value of x, that will return what s is. Until I return s to the main script, I will not have any s. So in fact, s over here should be replaced by e approx evaluated for n comma x. Okay. In fact, I can still write it as s, or I can write it as p, q, r, whatever. So let's call it as q. So q will be what? It will be e approx evaluated for n comma x, where n and x are these values. It has nothing to do with this. These values will be input into this function. This function will receive the values 10 and 1.1 from here. It will put it in this and it will evaluate this. After the evaluation of this, it will return the value of s as defined in this function scope, and the value of s is returned in place of this. In fact, to avoid confusion, I can call this m and y also. I have to change the print also because then it will throw an error. Okay, if I run this, it says the name x is not defined. Of course it is not defined because this had to be y. So good, even this works. So through this simple exercise we have seen how to convert a script into a function, because see, this has become very convenient now. The script doesn't look cluttered at all. The script only consists of 4 lines and you have a self contained function called as eapprox. So the variables inside eapprox, the variable passed to eapprox have no bearing on the entirety of the script. So I can have clean scripts operating over here. Okay. Alternately, once I've run this, this particular function eapprox now lies in the memory of IPython. So now I can go to my console and I can say eapprox 5 say 3 terms comma 1.2. It will give me 2.92. Okay. Or I can check the error. So I can write eapprox 3 number of terms evaluated at x equal to 1.2 minus np dot exp of 1.2. So the error is 0.4, and this is the absolute error. I mean, that should be obvious. Actually, when we increase number of terms, so suppose I say 30 terms, it says 0, but I mean it's a very small number, so it tells us 0. I can say 6 terms, so the error is already 10 to the power minus 3. Okay. So I hope certain very important things have been learned by you today, such as how to invoke the modules, how to vectorize, how to do everything. And in fact, we have not vectorized this. So okay, wait. So let me quickly show you how to vectorize this entire thing. So let me define another function def eapprox, but it is vectorized n comma x. It will also receive the same arguments. Now it will be what? So I equal to np dot a range 0 comma n. So once again, this I equal to np dot a range has nothing to do with this, because this is defined in a different function scope than this. Okay, this I will reside only in this function block, this I will reside only in this function block. So now let us do that vector operation that we had discussed. So terms equal to x to the power I divided by sp dot factorial I, and then return np dot sum terms. Okay, now I can, instead of eapprox, I can also call eapprox v. Let me run this, and there you have it. It gives the same answer. But I will tell you, we have not done timing and all, but the vectorized version, this particular thing works almost 10 times faster than this. And I leave this as a small home task for you to go to the documentation of Python, look up on the internet how to time your functions. It's not difficult. So with this we end this particular session.